Hi, my name is Lipika Ramaswamy. I'm an applied scientist at Gretel. Gretel is the synthetic data platform for everyone. And today we're going to talk about generating synthetic tabular data that's differentially private. So lots of words there. Let's break it down. Let's start with what is synthetic data. I will borrow a definition from NVIDIA, which is synthetic data is annotated information that computer simulations or algorithms generate as an alternative to real-world data. So the data can be of any type. It can be images, can be videos, text, tabular data, rows of a CSV, JSON, whatever it might be. So structured, unstructured, anything. Any type of data can be made synthetic. Now, the quality of that synthetic data depends on the type of algorithm that's used to generate it. There are a variety of algorithms that can be used. Some of them are statistical, some of them are deep learning based. So you would have commonly heard of generative adversarial networks, transformer-based networks, variational autoencoders, diffusion models. On the statistical side, there's probabilistic graphical models, Bayesian networks, copular models. So there's endless possibilities here, and all of these can be mixed and matched. So it's essentially a lot of really cool math that gives us synthetic data. And the goal of these algorithms is to learn sort of what the underlying distribution of this data is, right? So try to understand what's in the population that's represented by the data and to try to generate samples that look like the data. Now, why might we want to use synthetic data as an alternative to real-world data? There are a myriad of reasons. Some of the most common ones that we see at Gretel are folks either don't have enough of a certain type of data. So consider, if you're trying to study a rare disease and there are only n number of people in the world who have it, in order to generate more data, perhaps to perform a statistical study or to understand something sort of in a mathematical way, you might need more data. And one way of generating that is to, go out and find more people with that rare disease, but it may be infeasible to do that. So an alternative might be to pass the data that we already have about patients with this rare disease to an algorithm that can understand sort of what the underlying distributions are in that data and try to generate more samples like that. So that's one example. Another example might be there are privacy concerns related to sharing a specific type of data. So, again, a healthcare example is if we, let's say we're talking about a hospital that has patient records and they want to share it with researchers, but they can't because of privacy concerns. So perhaps synthetic data is a good alternative to share data with researchers. Now, one of the hallmarks of synthetic data is that the idea, the motivation is that this data is generated from scratch, such that no synthetic sample can be linked back to a single real sample. But there's no easy way to verify that samples indeed cannot be traced back to a single individual. And this is not surprising because really generative models are machine learning models, and it's been well studied and well shown that such models can memorize their inputs during the training process. So it could be that synthetic samples might reveal highly private information. So there are no great standardized ways of determining that on a cell by cell basis, but there's a lot of research out there on how we might do that. So privacy is still kind of a concern with synthetic data. We can't just say, oh, because it doesn't actually, perhaps link back on a record by record basis, that there's nothing that's revealed about the underlying population. So privacy is still quite important and it matters. So some really quick examples of why this is the case. For example, from LLMs, an individual's name, email address, phone number, physical address was extracted by researchers. The same thing was done with diffusion models with images. So that's it's a lot more tangible. It's real. Like you can see it. You can see exactly the original images in the generated set. And further, with tabular data, it's been shown by researchers that the membership of a given individual training record in the training set can be verified by attacks on a tabular synthetic data set. And so, this was tested on a bunch of different models that are GAN-based and Bayesian networks-based, variational autoencoders-based. And this was all for tabular data. So regardless of the modality of the data, there is still a privacy concern. But the good news for us is that if we want to bound that privacy leakage, or if we want to give ourselves a number on privacy, we can do that with something called differential privacy. Differential privacy has been around for almost 17 years now, or maybe more than that. But really, the idea behind differential privacy is that if you take an algorithm and it has some inputs, it has some outputs, if you change the inputs by just a little bit, the guarantee of differential privacy is that the outputs don't change by much. And so there's a number that quantifies sort of what the outputs are allowed to change by. And the way this all happens is by the addition of some noise into the process, into the training process of this algorithm. So let's say we're talking about generative algorithms, the input is a data set and the output is a data set. And we're saying that if you change the inputs, so let's say you add or remove one record from the input, we're trying to bound how much the output changes. So with differential privacy, if you're familiar with it, you might have seen two parameters that are typically associated with it. One is epsilon, and that is the ceiling on how much the probability of the output is allowed to change if a single training example is added or removed. The second one is delta, and it's sort of this external risk that exists no matter what you're doing with your data set, and it's unrestricted by epsilon. So typically we want delta to be very, very, very small. And in the case of these particular models, we want them to be smaller than 1 over the size of the data set, and typically a lot smaller than that. And epsilon is typically set to something less than or equal to 1, theoretically, for this definition to work out. Of course, in practice, we've seen epsilons up to 10 being used. So with this notion of differential privacy, how do we fit that into generative models? How do we make it work? We can take different mechanisms of differential privacy and add them on top of GANs or variational autoencoders or any neural network-based algorithms. And those have been shown to work sometimes, but they require a lot of configuration and just a lot of expertise in differential privacy and sort of training neural networks, especially things that are unstable like GANs. So what's an alternative? I suggest something called Gretel Tabular DP. So this is a model that we released a few months ago, and it's based on work straight out of academia, and it was born from this challenge that the National Institute of Standards and Technology ran last decade. And the goal was to try to generate differentially private synthetic tabular data. Their test bed was census data. And researchers came up with some very, very, very highly performant models for tabular data. And so the idea here, just very briefly, is it's a statistical model. There's no deep learning in here, but it's built with differential privacy in mind. So it's actually able to perform quite well. The idea is it's a 3-step process. It contains 3 steps: select, measure, and estimate. So first, let's say we have a data set. It has, n number of columns, m number of rows, and we say, okay, first, we're going to see across those n columns, can we select a subset of correlated pairs of variables? So not every single pair of variables, right? We're just selecting a subset using a differentially private algorithm. It's a differentially private version of the minimum spanning tree algorithm. So then we take that and all those selected subsets of correlated variables, and we measure their distribution. So you can think of this as like a massive contingency table, right? Like you have counts, you have a cross tabulation, you have counts of where one value was seen in one column and another value was seen in another column. And we add a little bit of noise to this to maintain differential privacy. And so we're basically creating these large contingency tables, and they're like multidimensional. And using those, we estimate a probabilistic graphical model that captures the relationship that's described by these sort of these very noisy measurements. So once we learn that probabilistic graphical model, we can sample from it. And those synthetic samples can sometimes be of very high quality and maintain distributions in the original training set quite well. So this is a solution. It works really well for data that is independent. So no time series data, nothing containing a lot of different measurements from the same person across time, that type of thing. So just keep in mind, it works really, really well when we have data that is independent across records. So let's try something. We'll use Gretel to generate synthetic data with Gretel Tabular DP. So here I have a data set. It's a data set that contains information on patients who underwent surgery for breast cancer. I got this from Kaggle. So there's a ton of information on expression levels of different proteins, the stage of the tumor, just information about their surgery, and their status at the end of the surgery or whenever it was measured. So there is some date information here, but there's only one record per patient in there. So, all right, let's take this data set and we're going to generate a new model with it. All right, so I'm using the Gretel console. You can use the same thing. It is incredibly quick to sign up and use the data set in a project. All right, so here I've selected the Tabular DP configuration, and all I've supplied is epsilon. So I'm saying, hey, I want a really academic epsilon. I'm going to use an epsilon of 1. Maybe that is kind of on the higher end on the academic scale, but we'll start there. And I'm going to have Gretel automatically determine delta for me. So it's automatically going to set delta to a value that is much smaller than 1 over the number of records in the data set. All right, and I'm going to begin training. So this process is pretty quick. A few things to note about this model. This model runs only on a CPU, so it's very efficient and it runs quite fast. So let's look at this data set really quick, right? There's information on age, protein levels, so a bunch of float values, a bunch of categorical variables, some dates, and another categorical variable. So fairly straightforward. And we'll see here that we're waiting for a worker to start. Now, so that we don't have to wait for this model to run, I've already gone through and run it once. So, all right, so we'll see here the training time was 3 minutes. For this model, it's exactly the same configuration that we just set, so it's an epsilon of 1. And we go to the activity. Here we can see some information in the logs. So, all right, we can see the delta was automatically set to this value, which is 0.00016. This is 1 over the number of records in the data set. There were about 330-ish records. So this is 1 over 330 raised to a power between 1 and 2. And that's to keep this value of delta really, really small. So our risk, our external risk, we want to really minimize that. So that's what we do with this auto setting for delta. All right, so we went through, there were 14 attribute pairs that were selected for measurement. That's great. It's not every attribute pair. And we can see that between the model starting to train, which was 1636, and the model ending, which is 1639, that was 3 minutes barely. And the model trained, records were sampled incredibly fast. And we have some information on the quality of these records. So this particular data set that we sampled, it got a quality score of 85. And this measures 3 things. One is how well are the correlations in the data set maintained. That's the field correlation stability. The second is deep structure stability, which measures sort of like if you look at the principal components of the training set and the synthetic set, how well do those two compare? and the field distribution stability, which looks at one-dimensional distributions and how well they were maintained. So this is just a high-level overview. You can look at our quality report for more info on that. Another model that I ran was actually using an epsilon that's slightly smaller. So let's take a look at that as well. So in the configuration, you can see I set an epsilon of 0.75, again, auto delta, so it should set it to the exact same value. And if I look at the logs and scroll all the way down, you can see that I got a synthetic quality score that was slightly less, which is okay. It's still marked as excellent by Gretel, but you can see there's definitely some loss in deep structure stability here. So there is always with differential privacy, always with privacy enhancing technologies, right? The more privacy you get, or the more privacy that you get in this quantified fashion, the more you can expect to perhaps lose in utility or usefulness of the downstream data, or rather the accuracy. So there's always this fine balance, but with something like Gretel Tabular DB in under 5 minutes for a small data set, we've generated synthetic records. So more patients who, or let's say synthetic patients who underwent treatment for breast cancer. And this might be able to provide us with a data set that we can share with researchers. So, yeah. Super easy to use. I highly encourage you to check it out. The underlying paper for this is very cool. So I would recommend looking at that as well. There's they're called marginals-based methods for generating synthetic data. And of course, we published a blog on Gretel Tabular DP outlining sort of all the details of this model, linking to the paper, and discussing it at a high level along with some experiments. So highly encourage you to take a look at those. Thank you so much for listening. I'm happy to answer any questions now.
Wow, that was an amazing talk. And I see we have some questions filtering in from the audience. So please join me in welcoming Lipika to the stage here for some Q&A. Welcome, Lipika.
Hello.
Great to have you here.
Thanks, good to be here.
Our first question today is, how do you choose privacy parameters for differential privacy?
Gosh, that is a big question that pretty much no privacy researcher wants to answer, because it is so dependent on the ultimate use of the data, or even the provenance of the data, right? So you might be in a scenario where you're working with like really sensitive information on people, or really sensitive like proprietary information, and you might want an epsilon that's really quite small. So like under 1. But in many cases, so in like many commercial applications, epsilons up to 10 have been used. So I think it really, really depends on the domain that you're functioning in. Unfortunately, that's the best answer that I have. But yeah, we build these algorithms. So a lot of algorithms are very good at providing reasonable accuracy for small epsilons. And then there are some algorithms that provide reasonable accuracy for slightly larger epsilons. And so your algorithm choice also, I think, probably differs there. But I'm happy to answer a specific question in the Slack about like your particular use case.
That makes sense. It seems like a lot of these things are quite context and use case specific.
Yep,
that's right. The next question is from Monish, and it says, can this work on semi-structured JSON datasets?
At the moment, if you're using Gretel, we would need, I believe we'd need a CSV and or JSON that's not nested. I think those are the only 2 cases in which it works. It may not actually work on JSON at the moment either. I don't know that off the top of my head, but if you can change a JSON into like a more tabular format, that might help. But I mean, JSON is always tricky, especially nested JSON. The other thing is with this particular algorithm, so the algorithm that we use for Tabular DP, the assumption is that you have variables in that like very traditional sense of like what is structured data, right? So there's like floats, ints, categorical variables, not necessarily free text. So that sort of unstructured side of things is maybe not the best as an input for this type of model. Perhaps something that's a little bit more like generative in nature, like a language model that can be trained with privacy guarantees would be more appropriate.
That makes sense. I mean, I think a similar question that we got on data is, how would you extend this synthetic data generation to time series data? And how well does it work for relationship extraction tasks or entailment tasks?
Yeah, so for time series data, I think the challenge is kind of different, right? Because often time series data means you have one time series from like one source, and you want to generate something that looks like that. So it might be a different source, but you want the same number of time points. And so if you think about like a generative algorithm, if trained from scratch, typically needs a lot of data, right? So if you have just like one series, to generate synthetic data from that is problematic. I think maybe not problematic, that's not the right word, but it's challenging. So for time series data, I recommend looking at Doppelganger, it was an academic paper that was published maybe like 3 or 4 years ago. And the open source implementation that was originally provided with that paper was written in TensorFlow 1. So change that, and we have an open source implementation at Gretel Synthetics that's in Torch, and we also offer it as part of our sort of product. So there's a lot of like automated stuff that we can do within our product, but certainly just checking out that model, especially when you have, for example, if you have data from, I don't know, multiple different sources across a large or long period of time, that might be more appropriate. But then there are also ways of chunking data. Also depends on kind of like what your end goal with time series data is. If you're looking for forecasting or prediction, I think that's a slightly different challenge that maybe Doppelganger isn't ideal for. But yeah, there are just tons of options. I recommend looking at Doppelganger depending on how much data you have.
That makes sense. Thanks for that recommendation. Kind of a broad question coming up next. Can you expand on the underlying differential privacy algorithm?
Yeah, sure. So the algorithm is based on a paper that was published by a group of researchers from UMass Amherst, I believe. It's called Winning the NIST Challenge. Let me pull up the exact name. Yeah, Winning the NIST Challenge, a scalable and general approach to differentially private synthetic data. So basically, it's an approach that's roughly in the community called a marginals-based approach. I would recommend, if you're at all technical and can stomach papers, I would recommend reading the paper. It is quite digestible if you work with sort of generative models on an everyday basis. But really, the two places that differential privacy is used is in the calculation of counts. And there are two places where this happens in the algorithm, which is the 3-step algorithm that I outlined on that final slide that I had. But exactly what I talked about is in that paper. And those 2 steps, they effectively involve getting counts. So like just building large contingency tables with noise. So it's differentially private counts, and counts are, they're kind of like, what's the word? They're like an easy algorithm to work with, to add noise into, because if you think of like the original definition of differential privacy, if you add or remove one record from the data set, like how much can a count change, right? Like it can only change by 1. It's not changing by infinity, or some value between 0 and infinity. 1 and infinity. It's always going to be 1. So that makes it a very convenient algorithm to work with. It's also very cool, the use of probabilistic graphical models in this sort of framework. There have been a lot of, there's been further work by the same group of researchers on this problem of differentially private synthetic data using statistical methods and not generative models, or like deep learning based generative models, sorry. So I would highly recommend reading that paper.
Awesome. Thank you. And our last question for today, we're running out of time here, is from Matt Casey. And he says, I recall reading something about this approach on 538 about how there are visible artifacts from it in the census data. What have they done to reduce those artifacts?
I don't know if I know exactly what 538 article this is, or if I've even seen this on 538, but a lot of this, this method was developed for census data. And in the 2010 census, some like kind of fuzzy version of differential privacy was used, but it wasn't really called differential privacy. It was just, when they saw certain cells were sort of had small counts, they were fuzzed, or like a value of, I don't know, 2 was turned into a value of 0, or maybe like 20. So that was kind of randomly done in a fashion that was not as calibrated as differential privacy. And so as a result of sort of all that noisiness that happened, and most people didn't even know about it, right? The differential privacy was used in the 2020 census. And so the methodology for that is, I guess, similar enough, but not quite exactly the same, because we're still reporting micro tabulations on the actual population. Like, we're taking every single record from a census survey that goes out, and then tabulating that to whatever block level. And so that's actually just like, that's taking counts and making that differentially private. But then there's a lot more work that has to be done in that case to make sure that, like, across tables, counts line up and whatnot. So like, there's consistency. There are a lot of great talks out there on how exactly this was done. I personally listened to one by Simon Garfinkel that was very detailed. So if you're interested in that, I would recommend looking up his work.
Okay, thank you so much.